yet, but it is. Most of the electronics, another 5 to 10 years from now, is not going to be what it looks like, what I shared with you, printed wiring boards components. Now it's all going to be conformal, 3D, flexible, wearable, printable electronics. So the entire form factor is going to radically shift from everything we know today. Okay. And then again, there's no way we're going to be able to cover all of that today because we also have a lab visit. That's from 2:30 to 2:30 to 3:30. So we're reconvening here after that. Oh, yeah, okay. So we'll cover what we can. Again, these are sort of specialty topics that I really don't want to get into detail. I just want to give you a general feel for what's out there. Okay. And then we'll move on to day 5. This is reliability, design for reliability, impact of manufacturing on reliability. So this is all reliability centered. Of course, I've been talking about failure mechanisms qualitatively all along. Here I'll give you a few examples of some models that are used to model these failure mechanisms and so on. So we'll talk about physics of failure fundamentals and then design for reliability. Just give you an example. We'll just talk about some lead-free assemblies. How do people design them for reliability? What kind of models do they use? And then we'll use those same models to look at how do people design accelerated stress tests. Obviously, you have to qualify your products in the lab in an accelerated period of time, shortened period of time, right? So you have to mimic a 3-year or 5-year or 10-year life cycle within a few weeks to a few months in the lab. How do you accelerate those tests or accelerate those failure mechanisms in a controlled manner? We'll talk a little bit about that. Again, each of these is like several days of lectures. I'm compressing them into just a couple of hours. Okay, and then finally I'll wind up with a little bit of comments about prognostics and health management. That again is part and parcel of the future of electronics. Electronics are so complex and the use conditions are going to be so diverse, there's no way the designer can cover all of that. So at the end of the day, we have to rely on real-time health monitoring to know what's the current condition of my product. Okay, so that's increasingly, used to be only high-end electronics used to have that, but now as the technology is becoming more affordable, it's spreading across even consumer electronics. And the economy of scale is also helping bring costs down. And then, of course, your favorite topic, final exam at the end of the day. Will that be either, I think it'll be tomorrow, last thing, right? Yeah, yeah. So once again, there's severe time constraints on how much material we can cover. So I'm going to keep it short. And especially in areas that are not my specialty, you're not really going to benefit a lot from me just repeating stuff that's out in the books. So I'm going to really shorten those, like high frequency packaging is mostly electrical design. I'm not going to talk about other aspects, mostly transmission line theory and stuff like that. For UEEs, that's, you do that for a living. Hopefully for the mechanicals, there may be some novelty over there, but I'll keep it at a very simple layman level because that's not my specialty. Okay. Okay, all that out of the way, let's get back to printed wiring assemblies. Yes, all right. Okay, oops. Okay, so printed wiring assemblies is basically just what I'm implying over here is just putting components together with the substrate, in this case printed wiring boards, and the process is either soldering or conductive adhesives or sometimes even just mechanical joints, okay? So, but predominantly what I'll be talking about here is soldering, okay? So I've just put up a few pictures of solders just to facilitate this discussion. So the number one requirement for solders is they have to form a good joint. So unless they wet the surface properly, the surfaces that they're bonding, in this case, the bond pad to the lead surface, okay, same thing there. In this case, there will be 2 bond pads. This is a ball grid array joint, component on one side, circuit card on the other side, with copper pads, several plated metal pads over there, and it has to bond adequately to those metal surfaces. So what does that mean? It's a 2-step process. One, it has to wet that surface adequately, and then it has to form a good intermetallic with that surface, right? So good wettability is a key part of it. Melt temperature is very important because if it's a very high temperature high melt temperature solder, you're going to take all of your electronics up to that temperature to melt the solder, and you'll damage a lot of your electronics. So low melt temperature is extremely important. Also from an environmental point of view, high melt temperature solder means a lot of energy consumption in manufacturing. Low melt temperature solder means you can bring down all your energy consumption costs. Narrow melting range, meaning as you're cooling it down from liquid to solid, most metals will pass through what we call a pasty range, where it's not quite fully as liquid anymore and not quite fully solidified yet. We want that range of temperature to be as small as possible. Why? Because during that period, the solder can still move, it's still semi-fluid, and the component can move around, and you can have misalignments, because your circuit card's actually moving in some kind of a moving belt in a reflow furnace. And if the solder doesn't solidify quickly, then while it's moving, components can shift around and you can get misalignments. So narrow melting range is important. And then all the life cycle properties. Once you form the joint, it has to be strong, it has to be fatigue resistant, it has to have good thermal properties to conduct heat, because some amount of heat, not a lot, but some amount of heat does go out through the leads and solder joints. Creep resistances, okay, so let's talk about it. Since we are talking about a low melt temperature material by definition, and we talked about this in day one, what does that mean? It means that at operating temperatures, even at room temperature, you're very close to the melt temperature. On a Kelvin scale, you're very close to the melt temperature, well above half the melt temperature on a Kelvin scale. That means your homologous temperature is above 0.5, which means the material is going to creep a lot. And that's a problem. If the solder, just under its own stresses, if it's going to keep on deforming, that's a big problem. Not only that, creep has well, how much it creeps has a direct bearing on how fatigue resistant it is. When we get to design for reliability and we look at the models, we'll talk about that. So high creep resistance is also important. But then you have to be careful. If you make it very strong, very creep resistant, then you create other problems. You shift the problem from the solder joint onto the chip, because now the chip is going to see huge stresses because the solder is so strong, not at all ductile, not at all creep resistant, so it does not stress relax. All the mismatch stresses are going to go onto the component, and that's going to cause problems in your substrates of the component, in the chips, and so on. Okay? So it's an optimization problem. And then, of course, cost and environment. Toxicity, that's one of the main reasons cited for getting rid of lead from tin lead solders. Of course, the replacements we have for it are not necessarily blameless either. They have their own toxicity issues. But the idea is to, in an ideal world, to find as low toxic impact on the environment as possible. So it's like underfills is a highly multidimensional problem. There are a lot of different attributes, and some solders are good for one reason but not good for another reason, and you're trying to find a good happy medium. What's a good solder today? Mostly in the lead-free world, post-lead-free, before lead was banned, it was mostly tin lead eutectic solder was the vast majority of electronic joints. Now it's mostly tin, silver, copper family. It's a ternary alloy. Tin lead was a binary alloy. These are ternary alloys, 3 ingredients, tin, silver, copper. And we'll talk a lot more about that as we go through. Okay, so here's the old tin lead binary. We'll talk about the tin, silver, copper ternary later on. So the tin lead binary, what we use generally is the eutectic version, which is right out here, about 63 to 64% of weight percent of tin, and the rest is lead. Okay, so you've got 10% on this axis. I'm sorry, percent of tin. So here it would be 100% tin and 0% tin over here. So this would be 100% lead, and this would be 0% lead. So right in here is the best choice for what reasons? I'm going to ask the students here. Given all the attributes we talked about here, which attributes? So basically what you're going to do is you're going to raise the temperature of the whole assembly to above the melt temperature, okay? And then you're going to cool it down, and the solder will solidify. So why not choose a solder of this composition, say 40% tin? Why 64% tin? Right, so low pasty range. If I cool from here, it starts converting from liquid into solid over here and does not fully solidify until here. So there's a big temperature band over there during which it's still in the pasty region and dangerous because components can shift around, right? So second reason, that's one. Excellent. Give me a second reason why I would rather have a solder here than a solder here. What temperature would I need to, let's say I take a 30% weight percent of tin. What temperature would I need to go to melt it? About 300 degrees C, close to 300 degrees C. What temperature do I need to go to here to melt it? The actual melt temperature is about 183. Typically you go a little higher than that, maybe about 200 degrees C. Usually they go a little higher than 200. Big difference in what temperature your electronics is going to have to endure during the reflow, and of course energy consumption, right? So for a variety of reasons, that is the obvious choice for, in the tin lead family. We'll come back to the SAC family later on. SAC is tin, silver, copper, tin, SN, S. Okay, so that's where the name SAC comes from. And there are SACs of many compositions. People vary the percentage of silver, percentage of copper. Then they put in some fourth microalloying element to control the microstructure, because there are a lot of microstructural issues with SAC solders. Okay.
Mainly because of your component characteristics, right?
Can you clarify that a little more?
So if I use an IC or resistor or transistor whatever in the printed circuit, each component has its own characteristics and the temperature.
Yeah, right. How much temperature it can tolerate, yes.
So most of the, any grade, if you take commercial grade or anything, it is designed for 200 degree. Go more than 200 degree, your characteristics.
You got it, yes. That's exactly right. Okay. All right. I'll skip over this one. This is getting more and more into details that we won't have the time for. Okay. And here are all the places in electronics where solders are used. Obviously for the solder joints of the assembly that we're talking about, die attach. Sometimes we use solders for die attach. Typically the die attach solder will be of a much higher temperature than the solder you're using for attaching the components to the board. For obvious reasons, you have to have that hierarchy of temperature, because you don't want the die attach to melt inside the component when you're trying to solder the component to the board. So successive soldering operations should be with lower and lower temperature solders, so that the previous solder does not melt again. We use them on lead finishes. We use tin plating, we use solder plating on printed circuit board pads, and on component leads. We use surface finish with solder. And then the solder ball that's in either flip chips or chip scale package or ball grade arrays, any area array package that comes with solder balls. The solder ball, of course, is made of these solders. The columns on column grade arrays are made of solders. And just like lead finish, the board finish, the pads on the boards are finished sometimes with solder, sometimes with other materials, sometimes with solder. Okay, so that brings us to the ternary solder. We're not going to go through the whole history of why it changed. We just don't have the time. It started, very simply, it started with legislation in Europe, and then quickly the market, it spread through the market, and now it's market driven. You just can't buy tin lead parts anymore. They're all, the whole supply chain switched over. Okay, so we'll talk about the microstructure a lot. It's basically a tin matrix, dendritic tin matrix. Okay, the tin solidifies in the form of dendrites, which are complicated structures. We'll talk about it. It's like Christmas tree kind of shapes. That's what it really looks like inside. If you look at it, tin with a microscope, really zoom in, it's not just a bulk homogeneous structure. It's got all these dendritic elements in it, and dendritic forms in it. And that has to do with the way it solidifies, okay, the way it crystallizes during solidification. And then embedded in there, what the silver and the copper are doing are forming intermetallic particles, and we'll see what those look like. Generally, the silver tin particles are nanometer length scale, tens of nanometer length scale. The copper tin particles are much larger, about micron scale, roughly micron scale. Okay, so here are some of the early, commonly used solders. The early solders were of this range. This is eutectic. This is the ternary eutectic. So when we look at the tin, silver, copper phase diagram, you'll find that that's the ternary eutectic, but there are problems with that. When you have that much silver in there, you get excessive silver tin intermetallics, and over time we have found that that causes a lot of reliability problems. If you have too much silver tin intermetallics, the solder fatigues too soon. So people started to drop the percentage of silver. It went from 3.9 to 3.5 to 3.0. From there all the way down to 1.0. Now it's like 0.1 in some applications. So people are progressively dropping the silver percentage. And again, there are a lot of drivers for it. Reliability is only one part of it. Cost is a huge part of it. And it turns out silver is not that much more friendly to the environment than lead. It's not as much of a risk to human beings, but because it's much lighter than lead, it leaches through groundwater system much more in your trash dumps where all the electronics get dumped. It leaches through the waterways into your water system. And marine life is very vulnerable to toxicity from silver. Turns out human beings are not quite as vulnerable as they are to lead, but marine life is extremely vulnerable to silver. So for a variety of reasons, some environmental, some cost, some life cycle considerations, the percentage of silver has slowly been dropping. Especially in portable electronics, it turns out that the drop resistance, ability to survive drops, correlates very closely with percentage of silver. That means how much silver tin intermetallics you have. Less silver tin intermetallics usually translate into better drop durability. So they have the portable industry has, and not to mention portable electronics is slowly getting cheaper and cheaper and cheaper. So that also cost of silver has to come down. So they're down to fractions of a percent of silver already. Okay. Okay. And you can see what the issues are. So the biggest concern is that all the SAC solders out there have a higher melt temperature than tin lead. So now the entire industry has moved up to higher melt temperatures, which means you need better materials that can survive those higher temperatures, both in the components and in the printed wiring board, because you're now going to heat up to about, well, the melt temperature is 217, which means you're getting up to about 230, 250 easily in order to solder it, which is substantially higher than tin lead as far as the components are concerned. Okay. And then again, the intermetallics that the silver and the copper are forming are causing reliability issues. Okay. Okay. So here's the ternary phase diagram. So some of you may be used to looking at phase diagrams. Some of you may not. I'm not going to spend a lot of time on it, other than to say when it's binary, then it's easy to plot it on a single axis like that. When it's ternary, it gets tougher. So this is the way ternary phase diagrams are represented. Are represented. You've got silver percentage on one axis, you've got copper percentage on one axis, and you've got tin percentage on the other axis. So the eutectic points are really in here. So if you zoom into this corner over here, okay, that's the eutectic point. Okay, that's where it converts instantaneously from liquid to solid at one single temperature. It's about, so you can see 220, 218, that's about 216 point something, okay? So at about 216 point something degrees C, a solder of that composition will instantaneously go from liquid to solid, no pasty range. But again, as I said, for a variety of reasons, we have dropped, well, some people actually used to use SAC 405, especially the semiconductor industry uses SAC 405 a lot, or used to. And partly because they wanted the higher melt temperatures, the temperature hierarchy that we've been talking about, because they didn't want solder joints inside the component to melt when the board level, second level reflow was being done. But it causes a lot of problems with excessive silver tin intermetallic, so that's a known problem. But the rest of the industry quickly dropped. They decided to reduce the silver percentage from 3.8 down to about 305. That does mean slightly higher temperatures. They live with it. That does mean a bigger pasty range. They live with it, mostly to get better solder reliability. Okay, so 305 is extensively used in the so-called high-rel industry, harsh environment, automotive, aerospace. They all use SAC 305. The consumer industry found that SAC 305 had very poor drop durability. Not consumer, the portable electronics industry has very poor drop durability. It has good ability to survive temperature cycles, but doesn't do very well in mechanical loading like vibration, shock drop. So they dropped, that industry dropped it to about 1% silver, SAC 105, and that stayed around for a long time. Now it's gone down even more. It's about SAC about 0.205, so 0.2% silver, So they're dropping silver progressively more and more. Then there are binaries also. There's tin silver binary, which is tin 3.5 silver, which is not a very good solder at all from a durability point of view. Then there's just tin copper binaries, tin 0.7 copper. That means 99.3% tin and just 0.7% copper. So there are some binary solders also, but it's typically the ternaries that are still dominating the market. Okay, and that's because the binaries have higher melt temperatures. Okay, okay. So that's the solder, and then you need finished material on the plating, both on the printed wiring board side, the pads on the printed wiring board, and the finish on the lead or the pad on the component side. So those finish is to basically promote a bunch of stuff. That finish allows good die attach, good wire bond at the level 1, but at level 2 it improves solderability, because otherwise the pads are basically copper, the leads are basically copper, they're going to oxidize. Just in storage they're going to oxidize. Or even when it's trying to go through the reflow oven and you raise the temperatures up, they're going to instantaneously oxidize. Of course, there are fluxes that are used to reduce those oxides during the soldering process, but even then it's very hard to do soldering to copper that is already oxidized. So you want to preserve solderability, so typically some finished material is put on top of the copper to reduce the amount of oxidation. And we talked about what those finishes are in the last session on Saturday, where we talked about materials like immersion tin, immersion silver, gold over nickel, variety of finishes, right? Okay. And the purpose of that finish is also to help in forming intermetallics with solder. So again, unless you form the right intermetallic between the solder and the base metal, you haven't formed a joint. So you cannot form too much intermetallic, then it becomes a brittle joint, but you have to form the right amount of intermetallic. So it's, again, a very complex optimization process. Not too little, not too much. Okay, so your reflow profile has to be carefully designed that it stays above melt temperature just long enough that you form the right amount of intermetallic. Too short, you don't form a joint. Too long, you have too much intermetallic. Okay. Okay. And then again, not every pad will be soldered. The remaining will just have the lead finish on it. So that's supposed to also prevent corrosion in the field. So you pick the finished material based on that. And it sometimes has, in high frequency applications, it has some electrical functionality also, the finish material. Okay, so we've talked about some of these finishes when we did the PWB session, so I'm not going to spend more time on it. And these are mostly informational. Here's what I'm trying to do today in the interest of time. Something that's just informational and you can read it just as easily on your own later on. I'm not going to spend too much time on it. Unless there's some explanation involved, I'm just going to say, okay, this is for you to look up later on, just a resource material, and we move on. Okay. Okay, but it's good to look at the categories that they've used to rate these solders. Obviously, the first one is solderability. Cost didn't quite make it to the top of the list, but it's up there. Okay. Shelf life. So that is these boards are going to be stored in the distributor's end before. So from the time the PWB manufacturer makes it to the time it finally gets soldered, assembled, there'll be time lag. So that's shelf life. How long does it sit before it oxidizes too much for good soldering? And then test probing is you're looking for functionality on the circuit card. So can the probes get through these lead finish materials and make good contact? For example, we talked about organic solder preservative. That means you're covering all the metal pads with a polymer coat. Well, you can't really probe very well over the polymer probe, so that's poor testability. Okay. Okay. Then how well does it survive well, initially the reflow cycle, and then eventually temperature cycles and power cycles in the field, and then planarization. So lack of planarity, so some materials will form very poor, give you a very poor planarity. That's a problem, because when you place your components, or when you're going to print your solder, you want a nice plane surface. All the pads should be at the same level, otherwise you're not going to be able to, when you print on it, you'll get solder joints of different heights printed on the pads, and that's not going to give you good, consistent quality solder joints. So planarity is also extremely important. So as an example, when you put tin solder finish on your boards, you actually have to go through a leveling step. HASL stands for hot air solder leveling. So it's actually leveled with hot air, otherwise you don't get good planarity after you solder plate all your pads. Okay. All right, and you can see some of them have come out with excellence everywhere. Some did not so good. Okay. Okay. This one, by the way, I'm not sure. I question that excellent. That's the costliest. Well, it's the second costliest of these options. ENIG is obviously electroless nickel and immersion gold. That's the most expensive, but this is the next most expensive one. So I'm sorry, cost-wise. This is the next most expensive one. So I'm not sure why they called it excellent. I question that. Okay. This was taken from another source, by the way. Okay. All right. So tin plating. So among those plating materials, board finish materials, lead plating and board plating materials, you can see that tin is one of them. So cosmetically, people used to like bright tin, but we learned soon that it has a whole bunch of problems. Bright tin has some additives in it to make it shiny and bright, but those additives have volatiles in them and it outgasses during soldering and there are problems with it. So industry has moved over a long time ago to matte tin, but tin has a big issue. We talked about it, tin whisker formation. So tin plated electronics run either plating on the leads or plating on the board. Over time, you're running the risk of forming tin whiskers that can then cause shorts, sparks, arcs, etc. Okay. And this is more discussion on matte tin. And then comparison of different plating materials. We did this one when we did level 1 packaging. We talked about all the lead frame plating materials. So in the interest of time, I'm going to skip over this one. We have seen this slide once before. Okay, tin whiskers also, we talked extensively about it. So tin plated components run the risk of forming whiskers. Okay, this whisker actually came out of a pore. This is tin oxide layer. This whisker came out of the tin pore, and you can see that with gravity it's collapsed. And now if it keeps growing, it can short against a neighboring metallization. Okay. And we talked last time also about some of the potential solutions. You try to reduce the amount of compressive stress, because remember I kind of drew a sketch of what are the steps that we hypothesize are what's causing tin whisker. We believe there are pores in the oxide layer. We believe there's compressive stress underneath, in the tin underneath, and it's that compressive stress that's extruding out these single crystal whiskers through grains that are correctly oriented. There are some grain orientations where you cannot grow whiskers very easily because that's plastic flow. Plastic flow only happens in certain crystal directions. So if the crystal underneath that pore happens to be oriented in the right direction and has the right amount of stress, it'll shoot out these single crystal whiskers. Okay. So the solution is to reduce the compressive stresses, both from internal plating process as well as from external sources. Use larger grain sizes, so there's less risks of running into a grain that's oriented in the wrong direction. Okay. And people have toyed around with certain amount of alloying. We've found that to be a mixed success. Sometimes it helps, sometimes it doesn't. Okay. Temperature hierarchy, I've alluded to this several times. This picture kind of puts it all together. So anytime you have multiple solder materials, for example, you have flip chip solder, this is a PBGA, flip chip PBGA, solder joints here. Obviously you want a higher temperature solder in the bump, because when you're doing the second level 2 reflow, putting these components on circuit cards, you don't want those joints to melt, right? So typically the highest temperature ones are high lead solders in here, and at the package level, either tin lead or SAC, as we saw. Okay. So lead free, it would be at the chip level. So there's not much of a difference over here, unfortunately. At the chip level, it's usually the binary, which is a little higher than that, about 250. And at the package level, it's this one. And I'm not sure why that became 230. That's not. That's incorrect. That's about 217 or so. Okay. I'll correct that later on and resend it out. Okay. Wetting. We talked a lot about the fact that you have to have good wetting. And here's a poorly wetted surface. Okay. And wetting basically comes because there's intrinsic surface energy. All materials have that, and that's because if you look at the nanoscale, the molecular scale, atoms at the surface have a different set of neighbors than atoms in the bulk. They have a different set of neighbors. So as a result, the energy of atoms on the surface is different, and that differential energy is what we typically call surface energy. And the surface energies have to match between the solder and the surface you're soldering on. Otherwise, this is clearly a non-wetted solder ball, and so you put a bead of solder on that plating. This did not wet. This one kind of partially wetted. This one wetted very well. Okay, so when there's good wetting, it'll spread out. So this angle, therefore, this contact angle, is often used as a metric of how good your wetting is. Okay, all right, and of course it's actually a tri-material interface. You have some air or gaseous medium here and two metals, so that's a tri-material interface. So that's why you're seeing solid to vapor, liquid to solid, so that's a liquid, solid, and vapor. So you have a tri-material interface, so you're looking at different surface energy terms for each of those combinations. Okay. Okay, and the point is that you're looking for a plating material and a solder material that wets each other well. Not all materials will wet each other equally well. It depends on the surface energy characteristics. Okay, then fluxes. So the solder material has to have fluxes because the moment you raise the temperature to melt it, at high temperature, the materials will oxidize instantaneously. So you have to have some chemical reducing agent right in there to strip that, to not allow that oxidation, and remove any prior oxidation that had occurred in storage. So both of those sources of oxidation are a problem. So fluxes are used for that. Variety of different fluxes. Actually, this itself is an entire lecture. I'm not going to get into it. Again, it's not my primary area of expertise. It's a rich chemistry topic. The chemists who make their entire careers work on fluxes for their lifetime. Okay, so if you go to a flux conference, it's amazing the level of sophistication that has gone into designing and coming up with fluxes. And again, typically these are water soluble, so you can clean them out. And then in places where you cannot clean them, so for example, that flip chip joint would be hard to clean, very little clearance. And now we are talking about micro bump joints, which are much, much thinner. These would be about 50 to 60 microns high. Micro bumps would be barely 20 microns high. So especially when you're doing die-to-die stacking, direct stacking, those are micro bumps with very little clearance, almost impossible to clean those. So for that you have low residue fluxes. So fluxes basically have volatiles. The volatiles will evaporate and you're left behind with solid residues. That's why you need the water cleaning. The water soluble ones need cleaning, and the low residue ones, specially formulated for low residues, are not cleaned. Okay? And the purpose, as we said, is to act as a reducing agent, and some other contaminations also, not just oxides, but the primary target is oxides. Remove those that had formed during storage and those that are trying to form because of the high temperature during soldering. Okay. Okay. So during the soldering, we also try to minimize the amount of oxidation that's going to happen. Where's the oxygen supply going to come from? The air around the electronics as it passes through the reflow oven. So sometimes we just use inert gases in the reflow ovens. So nitrogen is a very popular gas to be used for reflow purposes. So most reflow ovens that are commercially used usually have a nitrogen bath inside, so the soldering is happening in nitrogen. Okay, so the steps for the assembly is very simple. You would first put down solder paste on all the pads where components are going to sit. Okay, so this is the printed wiring board. How do you do that? Well, in low volume processes, you may actually dispense with a dispense head. You will go bump pad by pad. They're usually computer programs, so it goes pretty fast. Pad by pad, it goes through the whole circuit card and puts down the right amount of solder paste, metered right amount of solder paste on every pad. For high volume, you don't do that. You just use some printing process, silk screen printing, stencil printing. So here, for example, you're seeing stencil with openings wherever you want the solder to be deposited. So you would put down solder paste over there, and with what it's called a squeegee. It's like, you know, the foam pads that you use in your bathroom to just clean water. It's almost like that. So there'll be a squeegee that'll come across and take that solder paste all the way across, and wherever the openings in the solder will get deposited, and rest of the excess solder will get squeegeed off. and then you would lift the stencil off, and you'll be left behind with these solder sitting on the pads. Okay, so in this case, these are actually through hole, and but here are openings for solder pads. Okay, so you would need stencils that had those openings, so you could put those solder pads down. Okay, so SMTs will go through a reflow oven, surface mount. So these are surface mounts. Will go through a reflow oven, and the through hole ones usually will go through a solder wave process. So we'll talk about that very briefly at the end. Okay, so two different soldering processes. Okay, so here's stencil printing. Okay, you would basically put down, take the board, and you would either, so this will be a stencil over here inside, okay, and then you would put down paste, and you would squeegee that paste across that stencil. The stencil has openings in it based on your circuit card pattern. Let me show you a picture of a stencil. So stencils would look like this. There are a variety of ways of making stencils. These are metal stencils, and they have the openings wherever the pads are in your circuit card design. That's or wherever you want solder to put down solder in your circuit card design. That's where the openings in the stencil will be. The depth, the thickness of the stencil is very carefully controlled because that's how much paste you're putting down. So you want a metered amount of paste. You don't want too little, you don't want too much. You want just the right amount of paste. So the thickness and the size of these stencil openings is an entire art in itself. Well, science/art, okay? So a lot goes into designing stencils right. And if your stencil is not right, you're not going to get good solder joints. Then there's issues of cleanliness. Sometimes you put down the solder, but when you're removing the solder, stencil, if the solder lifts up with the stencil, that means the solder is adhering to the stencil because your stencil is not clean. So the stencil has to be cleaned, and the material of the stencil should be such that solder does not adhere very easily to it. Okay, because you want that solder pad to be left over there when you lift up the stencil, not lift up with the stencil. And as your pads get smaller and smaller, that gets harder and harder. You tend to lift off the solder. Okay, so that's where the rheology becomes very important. The solder paste rheology has to be right because it has to fill the opening in the stencil properly. It has to form a nice column over there, nice pad over there, but then it should not lift off when you lift off the solder. So the solder the paste composition, paste viscosity. And what is solder paste? Well, paste is basically little particles of solder, spheres of solder material, and flux, and some binders, complex rosin binders. And in a pasty form, that's how you lay it down. And then you reflow all those little solder balls, spheres, melt, and become a solid solder joint. Okay, okay. So it has a lot of critical requirements. The paste has to have the right rheology also, so it doesn't slump. So if you're making a fairly tall solder joint, when you lift off the stencil, the solder should not slump over there. It should stay in a vertical column, right? So there are all kinds of issues over there that are important. Okay, so these are mostly formed by electroforming. Most of them are made out of nickel. So again, there are a lot of details there which I'm not going to get into. Okay. Sometimes they're laser cut, either electroformed or laser cut. So there are a variety of different ways of making stencils. Okay. All right. Then you have basically, let's talk about. So you basically have a printed circuit card now with these solder paste on these locations on every pad, and now you have to put the components on it and then reflow it, right? So next step is to place the component. Apologize for that. It's a kind of a fuzzy graphic. I blew it up too much. These are basically pick and place machines. So these are highly automated in high volume production. So these are machines that are computer controlled. So the circuit card goes and gets registered in the right location. It's all vision assisted registration and so on. And then this machine goes and says, okay, I've got these 200 components that are going to go on it. That's already programmed in the memory. The components are all fed through cartridges into the machine. It knows which cartridge has which component. And the pick head goes and picks that component, puts it in the right place. Next component puts it in the right place. And it's basically a vacuum pick and place. So there's a vacuum chuck that goes and picks up the component out of the cartridge and puts it in the right place. Very fast. And these are computer controlled. They move extremely fast. But registration is important because misalignment is a problem. If you put the component down not in the center or tilted, there's a limited amount of self-centering that the solder will do. When it melts, it'll bring it back by surface tension back to location. But if it's excessively misregistered, that's too much. Okay, and then here are the kinds of cartridges. There are roll cartridges, flat cartridges, different kinds of cartridges in which components come packaged, and the pick and place machine will come and pick it out of there, or come and pick it out of this ribbon and place them on the board. Okay, and then there are tubes. There are various. These are basically feeders. So these are feeders that the industry has standardized. So there are various kinds of feeders: rolls, trays, tubes. This is how components come. Okay. And finally, just one slide. I'm not going to talk a lot about it. This is wave soldering. So for through-hole, so for surface mount components, this is how we do it. We stencil print, we pick and place, then we go through the reflow oven. I'll talk about the reflow oven in a minute. That should have been here. Where did it go? Oh yeah, reflow is coming next. But in fact, we'll come back to the wave soldering later on. Let's follow that train of thought we have been on for surface mount. So now I've placed the component. Now I have to go through the reflow process and melt the solder. So it basically has to stay. There are two main parameters. Well, there are multiple concerns over here. The most important one is you have to stay above the melt temperature of the solder long enough for good intermetallic layer formation. Otherwise, you haven't formed a joint. If you stay there too long above melt temperature, you'll form too much intermetallic. Or if you go too far high above the melt temperature, you form too much intermetallic and you're causing damage to all your electronics. So there's a process window that you want to stay within. You don't want to, the temperature must be high enough, not too low and not too high. And you want to be above that in that temperature range just long enough, not too short, not too long. So that's your process window, and you need to keep your process within that. Okay. And during that, and actually leading up to that process window is a preheating cycle, which we'll see soon. The preheating cycle is to prevent all the components from going through a thermal shock, so preheat a little bit. Also bake out any moisture that had collected in storage in the parts, in the PWBs and in the components that absorbed some moisture. You want to bake that out. If you don't, when you do that big spike to that temperature range, which is 230 degrees C or so, we talked about it in the last class. What happens to all that moisture? Popcorning. So you get explosive evaporation of the moisture, and that causes a lot of mechanical damage. So you need to preheat it. There's another very important reason for the preheat. So every step of this is engineered to the finest detail. Get one bit of it wrong, and you get a bad assembly. The other big part of the reflow is the flux that is in the paste is activated during that pre-reflow. That means before you get to melt temperature, you want to activate the flux so it reduces all the oxides. Okay? So again, it has to be long enough, not too long. If it's too long, the flux is going to get completely consumed, and then there's nothing left during the actual melt, and it'll reoxidize instantaneously. So that preheat cycle is also extremely crucial. Okay, so this is what a typical reflow oven will look like. That's kind of an old one that used to be in our lab. As I said, it's okay, let's talk about the reflow profile first, and then I'll come back to the characteristics of the oven. So here's the preheat cycle. Okay, remember the preheat is again partly to get rid of moisture, partly to activate the flux, and partly to get everything up to a certain temperature so they don't see a big thermal shock when you take it above melt temperature. So this is for tin lead solder. Melt temperature is 183 degrees C. So you get up a little bit higher than that, about 210 degrees C or so, just to make sure that there are no thermal shadows on the board, or even the ones in the worst thermal shadow of the board have reached reflow. What's thermal shadow? It basically means that two things. One, either sufficient energy didn't get in there and it didn't heat up, or there's so many heavy components, thermal inertia in that region of the board, that the temperature didn't reach that high because they acted as heat sinks. Okay, so the idea is you preheat, and then for a very short period, you get up above melt temperature, and then you cool it back down quickly. So this is that process window I'm talking about. You have to be a sufficient amount above the melt temperature for a sufficient period of time. Not too long, not too short, not too hot, not too cold. Just right. So this part of the process is important for the solder joint formation. This part of the process is important for the right flux activation, getting rid of moisture, preheating all the components, etc. Okay, so every part of this ramp, what's the ramp rate, how long, every step is important. Okay, so you can see there's a preheat, there's a drying cycle. During the drying, that's when you're getting rid of the moisture, but also the flux is getting activated. All of them are extremely important. So if I keep it too long here, say, oh, I want to dry it out really nicely, you have depleted all your fluxes, and by here, everything is reoxidizing again. So you can only keep it that long over there. Okay. All right, and then SAC will, of course, have to go higher. Melt temperature for SAC is 217, so you'll get up to about 245 or so. Okay.
So cooling is done separately?
Yes, so cooling, okay, now let's talk about that oven. So this is basically an assembly line kind of an oven, meaning there's a moving belt. You will put your components in from one side, they'll go in through their heating stages. There are 6 heating stages actually, because it has to go through these various reflow profiles. So it's moving at a particular rate, because how long it spends in each zone depends on the rate at which the belt, speed at which the belt is moving. And then there are different lengths of zones. So part of the time you're in this zone, part of the time you're in this zone, part of the time you're in that zone, and then finally you're in the cooling zone. At the very end, there's air cooling. And there again, you want to make sure that you're not in the pasty range, the solder is completely solidified, otherwise the cooling air jets will move your components, misalign your components. Okay? So that's why it's so important to have a very narrow pasty range. And then the actual reflow zone of it is also bathed in liquid nitrogen, gaseous nitrogen, inert environment, otherwise excessive risk of oxidation at that time. Okay? So may have, not all ovens have inert atmosphere, but some applications require that. And this is typically it's a multi-stage. There are different zones at different heats for these different stages. And the heating is usually done with a combination of IR and convection. So you're using IR to heat up the air or nitrogen, and then using convection to cycle that hot air under all the components so all the solder can melt. Did we lose power? Should I continue? Okay. All right. Okay. Okay. Let's skip over this one again in the interest of time. I got to keep moving. We just did this one. So this one actually I'd encourage you to look through. It basically says, I've already explained a lot of this, but it basically says if you get the ramp rate wrong or spend too little or too long, that means if you don't stay within this process zone and you're somewhere outside of that process zone, what are all the various defects that can happen. Okay, mounting defects, if you had excessive solder on the pads, that's why again the stencil printing part is so important. You got to get just the right amount of solder. Too much solder, you're risking chances of bridging with neighboring pads, especially in very fine pitch joints. That's a problem. Wicking, so if your lead plating is not the right plating, then what happens is the solder will wick up the sides, and then sometimes the joint gets depleted because the solder that should have been in the joint has climbed up the lead and is somewhere else in the wrong place. Okay. Residuals, you get solder splattering. So there's talk about that over here. So during the reflow process, if you heat it up too fast, then the solder basically splatters because all the organics are explosively volatilizing. And the solder at that stage, before it reflows, the solder at that stage is still just a bunch of spheres, small spherical particles, okay? Micron scale spherical particles, so held together with that resin binder. So if that binder explosively volatilizes, then all these little particles get released and you get splatter, solder splatter. So that's what you're seeing over here, solder splatter. So that means your preheat cycle was not good, B, you did not clean them off properly, bad rinsing. Okay, open leads, so that happens sometimes. It's called tombstoning. So what will happen is if once, I remember there's another set of joints here, so if these two pads, for whatever reason, there's temperature inhomogeneities, that means this pad was a lot hotter than this one, and that can happen, for example, if I had a big heat sink or another big component on the other side of the component over there, there's a heat sink that's taking heat away from this pad, and this pad won't heat up as effectively as the next one. So if there's non-uniformity of heat across the two pads, this solder melts and solidifies before this one can. So when that solidifies by surface tension forces, it pulls back on the lead because this one is still not solidified, and the component raises up. We call that tombstoning. Sometimes it raises up this way, sometimes for chip capacitors and all, we've seen them go all the way vertical. That's where the name tombstoning comes from. It looks like a tombstone instead of being a flat chip. It's standing up on one pad, okay? So it looks like a headstone of a grave, okay? All right, and then your printing process may have defects. You may have different amounts of solders. That also creates problems. Solder splattering, I talked about it. Insufficient flow. Insufficient reflow. It didn't reflow properly, so the temperature didn't get up to melt temperature, so the solder never completely melted, so it remains over there. Inadequate spreading, so if the wetting was poor on the pad, it didn't really spread. It stayed in the block that the print process had put down. It should have then wetted that surface. It didn't, okay? And then sometimes you may have skips. So during the print process, if your stencil got clogged, you don't get solder on some of the pads, and then you have solder skips. Okay, so there are a variety of defects. I'm sure you've seen every possible defect in your time on the line, right? Okay. So lead-free, as I mentioned, is not completely foolproof. It has its own problems. I mean, getting rid of lead has created its own set of problems. Now we need to solder at higher temperatures. Silver is not necessarily God's blessing to mankind or to marine kind. So it has its own environmental impact. Cost has gone up quite a bit, et cetera, et cetera. Okay. Not to mention the durability, the reliability of SAC solders has some significant disadvantages compared to tin lead. That we'll talk about when we get to track 5 or day 5. Okay. Well, I'll talk a little bit about it today, but more on day 5. Okay, so here are some of the, now that you understand the basic anatomy of what that assembly process looks like, back to our favorite topic. Well, and I've already talked about some of the defects, but some of the reliability issues, okay? So I talked about the fact that you can have popcorning. So if you had excessive moisture in your plastic packages, they could have damaged your packages. And that popcorning will not only delaminate, cause delaminations, it actually rips up soldered wire bonds and interconnections at the level 1. Okay. Okay, and that's kind of a cartoon schematic of popcorning. So there's moisture that's collected. There's typically already delaminations from the level 1 manufacturing process, and moisture during storage, moisture has already ingressed, and it's trapped in those delaminated regions. Okay, and then what happens is if you take it up to reflow temperature too fast, that vaporizes, that moisture vaporizes, creates this pressure dome, and then the plastic is not strong enough to contain that the stress caused by that pressure, and it eventually just cracks open and the moisture escapes from there. That is the process of popcorning. Okay, and it's a pretty violent process. We have actually studied these in real time inside electron microscopes, and it's a very violent process. And it damages lead frames, damages wire bonds, damages the die attach, and so on. And not to mention that your package is now cracked and useless. It's open to the environment. Okay. So that's these are basically talking about damage to the wire bonds, damage to the and delamination and package cracking. I'll skip over these. Okay, so this is some empirical studies of popcorning. Depending on the die pad size, how much water collects. So go back and think about it. Depending on the die pad size, that controls how much moisture. So it's a tiny die pad, you won't get too much moisture. Big die pad means a lot of moisture. You got to bake it out that much longer to get rid of the moisture before you reflow. Okay, that's basically what that graph is conveying. This graph, okay, talks about how much moisture you can have for different pad sizes. Okay, and the moisture sensitivity classification, therefore, because these collect moisture, they have to be stored in moisture-free environments. So different packages have different classifications. There's a class 1, class 2, class 3 storage. So more vulnerable components have to be stored in drier environment. They're usually packaged with desiccants and stored in dry, controlled environments. So that's what the classification is. Okay, we won't spend too much time on it. Okay. So you can see there are various moisture sensitivity levels that are in the standards. These are all in written up in standards. You can look that up. Okay. Okay, and this tells you what kind of soak condition you have to do to test for these different classifications. Okay. All right. So that's basically the storage I was talking about. So they have to be baked, pre-baked, and then sealed in moisture-sensitive, moisture-protected bags, moisture-proof bags, and then stored. So different components have different sensitivities to moisture. So that's what drives the classification level. And then when you're using them for assembly, sometimes you may have to rebake it, and they have to be stored in nitrogen cabinets and sometimes resealed if needed. Okay, if the allowable storage period is exceeded, then you have to redo the whole process. Okay, so these are all the various baking conditions. It's totally informational. There's very little discussion here, so let's skip over that. Black pad problem. Okay, so that's a problem that's actually at level 1, but happens during reflow, so that's why it's over here. We talked about the fact that we sometimes use, well, actually it's level 2 also, both. We talked about the fact that we use ENIG plating in a lot of cases. That's gold over nickel. And so this is electroless nickel, and there's phosphorus in the electroless nickel process. So so it's a process chemical. It's not a lot, but it's sufficient to cause problems. So what happens is it forms a nickel phosphide that actually forms a plating. It forms, when you put down the nickel plating, it actually deposits and forms a layer of nickel phosphides over there. And that causes a very brittle joint. When you do the soldering, that causes a very brittle joint, and that's a reliability hazard, known reliability hazard. So that's something that people control by controlling the chemistry of the electroless nickel process. Okay. Okay. Conformal coatings. So at the end of the day, when you're done soldering, so here's your printed circuit board now. You've got components on it. You've done all the soldering. Some applications require that you now protect this whole assembly from ambient moisture, and so they put down a conformal coating on top of it. Let me see if I have a picture of it. No, unfortunately, I don't have a picture. So it'll look, is there internet access over here directly online? We can just take a quick look at, let's go to images. I thought I'd put an image and I clearly missed it. Okay, so let's take a look at this one. Okay, so basically what you do is you put down this very thin polymer layer. So it's usually some kind of a liquid polymer that you would spray coat, okay, and then cure it. And sorry, let's enlarge that. Okay, so here the entire circuit card is covered with a uniform thickness of conformal coating. Why conformal? Because it's bending over all the shapes and all the components, and the entire product with all the components is now sealed under that layer of polymer coating. So that gives you a certain amount of moisture protection. Polymers are not hermetic. They will eventually absorb moisture, and moisture will eventually get in, but it gives you some amount of protection. Having said that, like everything else, it's a multidimensional problem. You put down a conformal coating for one purpose, to keep the moisture out. In the process, you may create a whole host of other problems, which means you have to get the coating just right. If you don't, here are some examples of problems you run into. If the conformal coating is too stiff a material, there are many different materials that are used for conformal coatings: epoxies, acrylics, parallenes. If it's too stiff and too thick, so again, the thickness of the coating is controlled by the process, by the spraying process. If it's too thick and too stiff, that means it's a strong coating. It has its own thermal expansion and shrinkage with temperature cycling. So it's going to be putting stresses from outside on all the components, moving the components around because of its own shrinkage and expansion. So if it's too strong, it's putting too much forces on the components during those thermal expansion and shrinkages. and you actually crack. So we see a lot of examples where fragile components like glass body diodes, for example, they are a known problem. They crack under conformal coats. There's another problem that happens. I have to draw a picture for this. So think about an area array component, okay, with solder joints under it, circuit card, and you put down a layer of conformal coating. The conformal coating is following the profile, okay? And some of it gets under it. During the spray process, some of it gets under it. Now when this expands, not only does the conformal coat expand this way, it also expands that way. What's happening here? The conformal coat is pushing up. When it expands more than solder. It's pushing up on the component. So now you have an unfortunate situation where with every temperature cycle, you're trying to pry open your solder joints, and it can only survive that so many hundred cycles. After a while, it fails. These solder joints start to crack, and that's the end of your assembly. Okay? So that means your conformal coat material must not be too thick. It should be as thin as possible. Well, not as thin as possible, because if it's too thin, then it cannot protect from moisture. Moisture will take very little time to penetrate through that. It must be of materials that have low moisture permeability, right? It must have not too high stiffness, mechanical stiffness, Young's modulus, and it should have not too high a CTE. The CTE should be matched to the assembly. So variety of requirements again. And then there should not be ionic contaminants in it, right? So it's an organic material after all. There are ionic contaminants in all organics. Those have to be controlled, because if all the organics get on the circuit card, now you've got loss of surface insulation resistance, leakage currents, corrosion. You've created a whole host of new problems by trying to prevent one. So for all those reasons, conformal coatings are used only when necessary, not always used. Okay. Okay.
Like for the IC, like when you're putting it on top of an IC, so the temperature released from the IC to the environment, then it will be blocked.
Oh, excellent point. The thermal aspect of it. I didn't even mention the thermal aspect. So now you're trapping in heat, and absolutely right. So especially if you have heat sinks and all, then of course it's very hard to put conformal coats on that. Excellent point. I completely missed that. Sorry. Okay. Sorry, Anandaroop. Bad. Okay. So that's pretty much this session. We're at 11. I think coffee break is at 11:30, so I'll continue on. Okay. Okay. Let's take a second, because this would be a good time to take a break otherwise. And then I'll move on to these other specialty packaging. I'm going to keep the high frequency packaging to the very end, because if we run out of time, I'm going to skip that one, because as I said, that's not my specialty. At best, I'll talk like a layman in that. Okay, it's a waste of your time. You can get that same material out of books. If you have time, I'd like to go over it, because there are some interesting aspects to it as far as packaging is concerned. But it's really an electrical designer's aspect, not a mechanical aspect. Okay, so I'll move that one to the end of today, maybe after the lab visit. If we have completed the rest of it, we'll do it after the lab visit. So what I'm going to do is move on to some of these, talk a little bit about power packaging, LEDs, some other miscellaneous stuff. So where are we? Okay, so let's take a break. We'll come back in 15 minutes and start here. Okay, thanks.
Just a quick one.
Okay. All right, so now on to some specialty packaging technologies. I'll just briefly touch on a few of them. So power electronics. These slides are from my colleague, Professor Pat McCluskey. He is the one who specializes in power electronics. So I took several of his presentations and kind of compressed them into a brief overview. The application of power electronics, you can think of any time you are converting AC to DC or DC to DC, any kind of power conversion in your power supply system, you have to worry about it. And the obvious places where they get used are power generation, could be solar power, could be wind power, oil exploration. Remember we talked about this is undersea. You also have on land, who goes way down below the soil. Okay, and so that's what's happening here. It's going under the water and then into the soil. and for kilometers and kilometers. So, and then you're dealing with power electronics down there. Obviously, they have to survive. So reliability is extremely, what's the word? A lot of stringent requirements on reliability, because you don't want electronics failing there, because then you have to retract everything all the way up for repairs and everything, right? So distribution system, generation system, transportation, aerospace, automobiles, buses, cars. So a lot of power electronics go into all of those, especially as we get into hybrid and electric vehicles, obviously, a lot of it. Smart grid applications, so a lot of applications for power electronics. And the idea is that basically it's conversions, right? So it's to process and control the flow of energy, AC to DC, DC to AC, AC to AC, DC to DC. So anytime you're processing your power inputs, and obviously you have a controller that controls that process before supplying it to the load. So that's any electronics that is required to do that is what we are terming as power electronics. And the issue, of course, is that you're dealing with high currents, high voltage, high wattage supplies, so your electronics have to survive that. So we're no longer talking about these very slender components, tiny slender components. We are talking about big, beefy wire bonds and very robust electronics. Okay. So you can look at parts, for example. So power converters consist of big, bulky parts, big, bulky bus bars for interconnections. So everything has to carry a lot of current, a lot of power, wattage, and so on. Okay. Okay. So here's a typical power electronic module. You've got circuit cards, you've got bus bars. In here you've got IGBTs, power diodes, handling hundreds, sometimes thousands of watts. Okay, and extremely high thermal challenge. So heat cooling of power electronics is a massive challenge. And I'll talk a little bit about it. In fact, Anandaroop alluded to some of it already in his course. I'll just briefly put up one or two slides where Pat McCluskey's also been involved in doing some of this work. So that's over here. So it starts all the way from integrated cooling right on the chip. So you already saw architectures like that Anandaroop put up, where you have heat sinks directly on your chip, to module level and box level cooling. You need extremely stringent cooling requirements at the kind of wattage we are talking about here. Okay. Otherwise, you've got problems with switching speeds, can't operate at high frequencies, and thermal runaway. So many of the failure mechanisms, and I'll talk about some of them, they're the same failure mechanisms that we see in the rest of the electronics, but because of the high temperatures and the specialty materials here, they require some special handling. Okay. Okay. So you already saw models like these. So people who are doing the thermal management of power electronics are doing the same kinds of models that you talked about yesterday. So you build up thermal network models and then try to design your cooling system, your cold plates, your cooling systems, liquid cooling. All of that is designed based on what the junction temperatures finally have to be at. And some of these power electronics are in very harsh environments, as I mentioned. So go back here. These are in exposed environments, very high temperatures. So trying to manage junction temperatures there is not a trivial challenge. Same thing with automotive. So if it's some of the automotive electronics is in pretty harsh conditions. Okay. Okay. All right. So here are some typical interconnections. So, and the failure mechanisms, again, like I said, there's nothing intrinsically different about the failure mechanisms. You get wire bond failures here. These are typically not, well, some of these are potted, molded over, but many times they're not, okay, in power electronics. So these are usually much thicker wire bonds, not the thin kind of wire bonds that we use in microelectronics. These are pretty thick wire bonds and bus bars. Sometimes the interconnections are very, very thick, okay? And then you get failures of die attaches, you get failures of the substrates. The substrates, sometimes the conductors will delaminate from the dielectrics. Sometimes the dielectric itself will fracture. And we'll talk about some substrates in a couple of slides. And then the die attach failure is a big issue. We'll talk about that because, again, the temperatures are so severe that we get die attach failures. And same thing with wire bonds. We've talked about that before. Flexure fatigue of the wire, failure of the bond itself. So intermetallic formation at the bond itself, all of those are problems. Okay, so again, this is just a repeat of what I said in the last slide, so let's skip over that portion. Let's briefly talk about the new information here is that planar interconnect. Let's briefly talk about that. So there are architectures when you have to get to real low profile packaging. There are architectures where you don't use big wire bonds because these are big wire bonds. So the height is pretty significant in terms of electronics assembly. So when you want really low clearance packages, both for electrical and geometric reasons, then people go to planar pack. So here you're putting these bus bars directly onto the chip without a wire bond interconnecting them. You have other direct contact mechanisms through vias and so on. So you use copper bus bars with vias directly on your interconnection points on your dies. So, for example, since some of you have, how many of you worked in GE? I know you have. Anyone else worked in GE at some point? No. GE makes a planar module, which they call actually power overlay, POL. They market it as the POL design. And we actually did some studies on that. And there the challenges are the vias will fatigue because you're talking about extremely severe temperature cycles. The vias, either the via barrel will fatigue or the via will pull away from the die and so on. So planar packs have, so that interface between the silicon and copper where you make the via connections are sometimes a challenge. Electromigration, you're talking about very, very high current densities traditionally. That's why your conductors are so thick. But even with such thick conductors, you're sometimes pushing the limits of the design and current densities are so high that we do see electromigration. Not just in conductors, where we see more often are in the solder joints. Believe it or not, there's electromigration even in solder joints. So the current density sometimes in solder joints will be so high that the same thing that happens in aluminum traces, it knocks out metal ions from the lattice, same thing happens in solder joints. It knocks out metal ions from the tin lattice, and you start to grow these depleted regions, which then are even more vulnerable to thermomechanical cyclic fatigue. And they kind of hurt each other, so they collaboratively fail the solder joint. Also at those very high temperatures, you get excessive intermetallic growths. So that embrittles the joints. If there's any kind of harsh mechanical stress, you get vibration failures at those intermetallic joints. Okay, and which I'll talk about later on. We talk about, loosely, we talk about, oh, it formed too much intermetallic, got brittle and failed. Strictly speaking, it's not that failure. The mechanical stress failure is not because there's too much intermetallic. It's more, it's a little more complicated. I'll show you examples later, but I'll just draw a picture to explain for now what happens. So if you think about the intermetallic layer, it's a very wavy, scalloped kind of a material that forms. This is solder. Is that big enough? Can you read it at the back? Yeah, okay. This is copper, right? And let's say for this combination, if this is a sack solder, okay, then you form tin copper, so actually it's Cu6 SN5 intermetallics, and you form some silver also that forms off of it, Ag3SN. Okay, so you form some complex intermetallics at that surface. With excessive heating, what happens is not only does it grow thicker, but more importantly, it loses some of that scallop behavior and becomes more smooth. Okay, the dips fill up, okay, and the overall surface loses its waviness. Not loses, but reduces its waviness. And you can see that very clearly here. Look at this one. Let's zoom into some of these. So you can see how scalloped this one is. But over time, look at what happened. The thickness grew dramatically, okay? And it's not as wavy anymore, not as scalloped anymore. So why is that important? Now if you start a crack, so the high strain rate failures are usually not just in the solder, but oftentimes right at the interface. In fact, you can see in this one, this is of course electromigration, but you can see it separated from the intermetallic layer, okay? So what happens is these high strain rate loading, typically the cracks will be at that interface, and then it can propagate very easily. If it's not scalloped, it can propagate easily. If it's very scalloped, it's a tortuous path. It takes a lot more mechanical energy to propagate it. Effectively, that gives you a higher fatigue resistance or higher fracture toughness at that interface, okay? But once that surface becomes more smooth and flat, it's much easier to zip a crack through, so the apparent fracture toughness drops. So that's the real reason why excessive intermetallic is bad. Not because of the thickness, but because you've lost the waviness on the interface, okay? And that's a discussion you hear a lot of times. People say, oh, I had too much intermetallic. No, 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 you didn't have too much intermetallic. You had too poor an interface of your intermetallic, okay? Okay. The thing is, it goes hand in hand, so there's a correlation. If you had too much intermetallic, chances are you also had a poor interface. Okay. Okay, and then so in these planar modules, we no longer use wire bonds, as I said. So the way we interconnect has now totally changed. We use some kind of a die-attached kind of material or diffusion bonded, solid-state diffusion bonded interconnections. And we bond connectors this way rather than use wire bonds. This picture is not, oh yeah, you can see it over there, instead of using wire bonds, okay? That's not millimeters, that's microns, sorry, okay, yeah. Okay, I should change that. Let's do it right now, otherwise I'll forget to go back to it. Here. That got converted when converting fonts, it got converted. Okay. Okay. So the kinds of materials people are exploring for these kinds of interconnections now are sintered materials. You need high temperature joining materials. So for some applications, all the solders we have today are no use. Solder still melts at about 200 and something degrees C, and many of our power electronics applications require temperatures well beyond that. Okay. So the kinds of materials we are exploring there, so we still have the solders and the adhesives for the low temperature applications, but for high temperature applications, we are looking at these classes of materials. So in my group, we do quite a bit of work with researching sintered silver. So here what happens is, instead of solder paste, you put down silver paste, pure silver particles, and then you diffusion bond it under some pressure. It's a problem. How do you apply pressure in electronic joints? I mean, you can't press some components that easily. So it's a problem. We can only do this in certain architectures. For example, this kind of architecture is ideal for it. So these kinds of interconnections, you can put pressure. So that's a good application for sintered silver. So what happens over here is the silver particles are nanoscale to start with. So you have basically have a resin binder with nanoscale silver particles dispersed throughout that. They're typically spherical particles. But why nano? Because the surface to volume ratios in nano is extremely high. So now you have a lot of surface contact between neighboring particles. And what happens when you have good surface contact? Interdiffusion, self-diffusion between the silver particles. And with a little bit of pressure, a little bit of temperature, you can easily get solid state diffusion because of the high surface area, and they bond. Once they bond, you now have a semi-porous material, and higher the bonding pressure, lower the porosity, but you have a semi-porous material that's now just directly bonded silver. Now it's not going to come apart until you reach close to the melt temperature of silver. So in solder, the problem is you're always close to the melt temperature of solder. By close, I mean above half the melt temperature on a Kelvin scale. Silver is 900 to 1,000 degrees C melt temperature. So now you've got a high temperature material. The disadvantage is it's a porous material. And as you know, porous materials have mechanical fragility, right? So there are some issues with it, but excellent for thermomechanical cycling. Any high strain rate loading, it's a problem. But for thermomechanical loading, just temperature cycling, it's a very robust material. It doesn't creep as much as solder because it's far away from its melt temperature. It doesn't fatigue as easily under temperature cycling because, again, it's so far away from its temperature, it's creep resistant, so you don't get a lot of creep strains, cyclic creep strains. So it's a promising material. It's being used more and more and more. Cost is a problem. Okay, so only for critical applications, not for every application. And then comes the issue of how well does it bond to the plating. So typically we put silver plating whenever we have to use sintered silver joints. This TLPS, transient liquid phase soldering, is a very exciting technology. This is my colleague Pat McCluskey, who made these slides. He's one of the pioneers in it. There are several people researching it. He's one of the pioneers in it. He holds several patents in it. I'll talk about that. It's a complicated technology. I'll talk about that separately in a different slide. Okay. Again, I don't want to spend too much time on it, but just enough to let you know where some of the research is going on. This one is on silver sintering. So this just says that it's sintered at these kinds of pressures and temperatures. And then once it's been sintered, now it's a high temperature material. Okay. And it sinters at this temperature only because it's got so much surface to volume ratio. And the organic binders, the other thing that's happening at that temperature is all the organic binders that when you buy the sintered silver, it's like a paste. So all the organic binders have to be burnt off. There are two kinds actually. In one kind, you burn off the organic binder completely. In the other, the organic material stays. So that one is more like a conductive adhesive, silver-filled conductive adhesive, rather than a sintered silver joint. So both kinds are used. Okay. All right. Let's. This, by the way, gives you the reflow temperatures. Not quite. It's giving you the melt temperatures. The reflow temperatures, you have to add a small delta on top of that. But it gives you some idea of different classes of materials. So tin lead solder has the lowest melt temperature of all the commonly used reattach, other than polymer attach. Okay, conductive polymers would be a lot cooler than that. So that's SAC 305. This is high lead solders. Okay, so that's about 93% lead. So that's close to 300 degrees C melt temperature. Okay, that's why high temperature applications require high lead solders. Bismuth silver alloys, again, a lot of groups are researching that. We did some studies ourselves. It's a very good high temperature solder in terms of thermal capability, but very brittle, unfortunately. So cannot withstand mechanical stresses, shock, drop, vibration, cannot stand it. Okay. So these are the so-called hard solders. Gold tin, gold germanium. These are used as die attach materials extensively because you want high temperature materials for die attach. Think of the temperature hierarchy. You want high temperature materials for die attach. So these are used, in some applications, these are used for die attach materials. This one is not very common. Zinc aluminum is not very common. It has some corrosion issues. So neither one of these, zinc aluminum or zinc germanium, hasn't become that popular. Sintered silver is outstripping pretty much all of these in terms of popularity for high-end applications. Okay. The TLPS technology, we could easily get lost in this. I'm going to keep it very simple. So the technology is as follows. You put in two-phase material, A and B, and it can come in various configurations. It can come as powders in a matrix, okay, particles in a matrix, or mix of particles, or sheets, sandwiches, okay, comes in various forms. And the idea is there's a low melting phase and there's a high melting phase. So B is typically the low melting phase. Let me see what his notation here was. No, B is the high melt temperature constituent here. A is the low melt temperature constituent. So when you melt it, the A melts all around the B, okay? And now the A is in liquid phase, the B is in solid phase. But as long as one of the phases at that interface are in liquid form, you can get rapid interdiffusion and rapid intermetallic formation. So we choose the constituents A and B carefully so they form good intermetallics. Okay? For example, copper and tin will form excellent intermetallics. Nickel and tin will form excellent intermetallics. So the low temperature material here is tin, high temperature material here is copper. So the B particles would be copper, the A particles would be tin, the A would melt, the tin would melt and form this pool around the B. Interdiffuse very easily. Now it's liquid phase interdiffusion that's very fast, forms these intermetallics. And if you keep it heated long enough, eventually it'll consume all the B and form this intermetallic, copper tin intermetallic. And the melt temperature, so all that is happening at the melt temperature of A, which is a low melt temperature material. Typically in this example, tin, which melts at about 250 degrees C roughly. Okay? So at 250 degrees C, you form these intermetallics, and that intermetallic, copper tin, has a melt temperature of 12 to 1300 degrees C. So by low temperature processing, you've produced an extremely high temperature joint. Okay? So that's the concept of transient liquid phase because A is in liquid form, liquid phase sintering. There are some issues with it. Well, the advantages, you've got excellent for very high temperature applications. The disadvantages are more on the mechanical side. Intermetallics, as you know, are very stiff, very strong, very brittle. So think about if you make a die-attached material out of this. Now you've got a very unyielding, stiff, strong material under the die. All the thermal expansion mismatches are going into the chip. The good news is that its CT is pretty close to that of silicon. Most intermetallics are 5 to 6 parts per million per degree C. Silicon is 3 to 4. So there's not a big CT mismatch with silicon, but there's a lot of CT mismatch with everything else around it. So some of that makes it back into the silicon, and there's no stress relief because it's so rigid, there's no stress relief. So for example, if the board warps, remember I told you packet sometimes warps, this will transmit all the stresses into the die, no stress relief, and it'll fracture the die. So, and then because it's brittle, any shock, drop, vibration, high strain rate mechanical stresses, these are a little bit vulnerable, okay? It's not that bad because my colleague, Professor McCluskey, has done extensive amount of testing actually in my lab because we have all the vibration shakers and drop towers and everything in my lab. So he's done a lot of testing of this and they're coming out pretty good. They're still not, maybe the mechanical durability won't be as good as, for temperature cycling, they're excellent. But for mechanical shock, drop, and vibration, they won't be as good as more ductile die attach, but good enough for most customers' requirements is what we're finding. The next generation TLPS are actually talking about putting in ductile particles, so there'll be 3 phases, A, B, and then C's. So the A and B will not interact with the C. The C will be some other inert material, but soft and ductile, so that this will basically be a high temperature material with ductile particles like lead. Well, it won't be lead because lead is banned, but materials like that, ductile particles embedded in it, so that gives you toughness. So cracks that start to form will get arrested by those ductile particles and won't propagate all the way through. So that's the next generation TLPS that people are exploring. That's the overall concept. I'm not going to get into any more detail because that would take a long time. Okay, substrates. So substrates fail, unfortunately, because again, you're talking about extremely high temperatures, severe temperature cycling. And typically for power electronics, there are 2 kinds of substrates that get used. Either it's direct bond copper or direct bond aluminum, okay? Which means the metal layers, the conducting layers, are either copper or aluminum. And there's the dielectric layers. The dielectric layers are typically ceramics, alumina, aluminum nitride. So these are expensive, high-end substrates, but that's what you need for power electronics. But the downside is because these are ceramic substrates, they're brittle. So anytime you have stress concentration, think about this corner, there's a big CT mismatch between copper and alumina. And so right there's a stress concentration, and cracks will form over there. So this is very typical. We see these kinds of cracks forming in either DBC. DBC stands for direct bond copper. DBA stands for direct bond aluminum. Only difference is that this metallization will be aluminum there. So in either of these classes of substrates, we do see a fair amount of vulnerability to cracking. Okay, let's move on. Other PWB failures, we have already talked about many of these: conductive filament formation. Those are in the buried layers. You get fibrous debonding and copper migrating. Then all the usual problems we see in regular electronics, you see in power electronics also: solder fatigue, plated through hole and via fatigue, corrosion, and dendritic growth. Okay, so these are electrochemical migration. So these are not unique to power electronics, but because of their harsh environments, fairly high risk. Okay, IGBT modules, they have their own problems. So that stands for, the acronym is given over here, insulated gate bipolar transistors. Remember we talked about bipolar transistors and field effect transistors. The problem with classical bipolar junction transistors is that the switching speeds tend to be low. So here with special insulated gate technology, they're able to get pretty high switching speeds at very high currents and voltages. So that's what IGBTs are used for, as switches, high-speed switches in electronics for converters and other inverters, converters, other technologies. And you can see standard BJTs would be down here, power MOSFETs are down here, And then IGBTs can carry even better voltage and current ratings and still retain their speeds, switching speeds. Okay? So they kind of combine the advantages of fast switching that you get in field effect transistors and the high current carrying capabilities that you normally get in standard bipolar junction transistors. The technology is pretty interesting. There were a couple of slides Dr. McCluskey had put in on the silicon level technology over there. In the interest of time, I took that out. But the gates are very specially made over here. The insulated gates are very specially made over here. They're usually trench gates, which is very different from conventional logic ICs. So these are deep gate trenches that allow these guys to operate properly. Okay, on the packaging side, we already talked about it. You either have wire bonded packages or you have these planar packs. So I talked about the GE power overlay module that falls in this category, press pack modules. There are no wire bonds here. You're making direct contact, okay, to your chips. Whereas here, sometimes there are vias in here. In this simple cartoon, the vias are not shown, but usually there'll be vias going through over there, as opposed to conventional wire bond modules. Except these wire bonds are very thick, very robust, order of magnitude thicker than conventional ICs. Okay. All right. Okay, the next 3 sets of slides, 3 or 2, let's see, 2, is basically a laundry list of what are all the various failure modes and degradation modes that we see in different parts of these power electronics modules. Okay, so this is part of a study that actually a group of students were doing a paper study for one of Dr. McCluskey's courses. So we have, I told you before, we have a packaging course, which is basically an expanded version of what you guys are getting here. So as one of the class projects over there, students had done a paper study of what are the different literatures and different failure modes, and they had put together these 2 tables. It's a nice summary of all the various issues, so I've included it over here for you guys as a resource material for you. We won't have time to go through each and every one over here right now. Okay, so I'll just leave that as resource material and move on. So basically power electronics, it basically says that we're looking at new materials, sintered materials, TLPS materials, new architectures, moving away from wire bonds and everything to planar packs. And the IGBT technology is also evolving. So they're going up to higher and higher speeds and higher frequencies and higher current densities and wattages. So they're actually making some pretty innovative changes to the IGBT technologies at the silicon level. And then people are talking about high temperature, high band gap materials switching over slowly to gallium nitrides, which has its own set of challenges because gallium nitrides have much higher defect densities, dislocation densities, than silicon does. So that affects, unfortunately, the electrical characteristics. So they call them threading dislocations. And they evolve because of the high stresses in these. Their density grows, dislocation density grows over time, and slowly the functionality, electrical functionality drops off. So gallium nitride has its own set of issues. But you have the advantage of wide band gap materials over there, so those are getting more and more popular. Okay? So that's really where all the research is, and as the temperature levels also go up, we're going to keep people like Anandaroop and his group busy. A lot of thermal challenges. Okay. Okay. That's power electronics. Let's move on to the next topic under specialty packaging, and that was LEDs and PVs. So again, I am not the primary expert over here. I know just enough to be dangerous, okay, to use a slang. This is thanks to the second person here, Professor Bhattacharya. His group does extensive amount of research on packaging of LED technologies. And when I say research, we don't mean, in CALTS, we don't come up with new packaging architectures. Our job is to find what are the reliability risks in packaging architectures that different groups are proposing. So most of our focus is on degradation mechanisms. So that's where Professor Bhattacharya does a lot of his work. So LEDs, and I'd mentioned this before, basically it's when, remember we talked about the fact that you're generating charge carriers in transistor devices. In p-n junctions, you're basically creating holes on one side, excess of holes on one side, excess of electrons on the other side, charge carriers, right? And that's how your semiconductor is actually conducting in your IV curve. That's how they're conducting. But we also talked about the fact that these charge carriers, once you create them, either by some form of excitation, thermal or electrical excitation, you create the charge carriers. They don't last forever. They eventually decay, meaning they fall back from conduction bands back into valence bands, or holes and electrons will recombine. There are various forms of decay by which they eventually go away. But where does all the energy go? You gave them energy to create those high energy mobile electrons and mobile holes. Where does that energy go when they decay? Well, that comes out in some form, usually temperature. That's why electronics runs hot. But sometimes photons. So not just phonons, but photons. Phonons would be heat, photons would be light. So LEDs, so some particular kinds of semiconductors are better at giving off the energy as photons rather than phonons. Those are the ones that we use as LED devices. Okay? So particular kind of doping, particular kind of semiconductor materials favor photon emission rather than phonon emission. So that's basically all it is. It's a semiconductor diode, p-n junction, that emits typically narrow spectrum light. That means depending on what material you're using, it'll emit photons of a particular wavelength. That means light of a particular color will come out. So you have green LEDs, blue LEDs, red LEDs. They're tailored to give out energy only of a certain bandwidth, okay? Photons only of a certain bandwidth. And then by combining different color LEDs together, you can produce combined white light and other combinations of colors, okay? Luckily, it turns out that LED devices are usually pretty long life. So think about your incandescent bulbs that we used to use. Some of you probably haven't seen them anymore. They go out pretty fast, right? But in my lifetime, most of my lifetime, we used incandescent bulbs. They last for roughly how long? Maybe a year or two at most at home, okay? Then we moved over to CFL lamps. Typically they last better. Remember, you buy a CFL lamp, they give you a warranty. They write the date, sale date on the back. The idea is that they give you much better warranty, longer warranties. Although, strictly speaking, they honor only a 1-year warranty, but in reality, they're supposed to last quite a bit longer than incandescent bulbs. Then comes LED lights. I'm skipping over the halogen lamps. They're also that family of lamps. I'm skipping over that. LED lamps, those last much, much longer. They're designed to actually last about 50,000 hours, okay? And that's because intrinsically, these are very stable devices. They don't degrade very easily. What dies is the packaging, not the device. The device is very stable. So in all the accelerated testing that we do for LED devices, we're never able to fail the device. We fail the packaging. Okay, all the degradation modes we see are the packaging. Okay, so I'll skip over that. It's basically you've got forward biased p-n junctions, and basically as they recombine, as the holes and electrons recombining, they give out that excess energy in the form of visible light, and you can see that you have different wavelengths over here producing different lights. Okay, so depending on the lattice constants of the semiconductors that you're using and the energy at which you're using it, you get different colors. Okay, and you can see what are some of the materials that are used. Gallium nitride is a common material, aluminum nitride, aluminum, gallium, indium nitride, phosphides, aluminum, gallium, indium phosphides. So there are complex semiconductors that are compound semiconductors and complex combinations of compound semiconductors that are typically used for these. Okay, indium phosphide, gallium arsenide are down here, indium nitride is down here, and so on. Okay, and there's a rough relationship that you can actually derive. So depending on what the band gap energy is, you can roughly calculate what the nanometer of the photons are going to be. Okay. Okay. And here the same information that's graphically here is put down in tabular form over here. So you can see that red, well, in the red and infrared region, typically they use aluminum gallium arsenide. Then green is phosphide. Okay. Then you get to orange and yellow range, that you add indium into that, okay? So slowly you're changing the lattice constants, so, and with that the band gap energies so that you get wavelengths of different colors, and so on. So you could keep going down the list. You can see the blue LEDs are all silicon carbide, alumina, or zinc selenide. Okay, so that's where most, and indium gallium nitride. So those are mostly the blue end of the spectrum. Okay, this one I don't fully understand, so I'm going to skip over that one because there are other technologies to produce white light that are usually used commercially. This one is not used that much commercially, but apparently there's a combination of gallium nitride and aluminum gallium nitride, particular technology that provides white light, but that's usually not how commercial white light LEDs do it. They do it differently. Okay, so here's what a typical packaged LED device looks like. And again, I'll repeat that this part of it, the LED device itself, typically has 50,000 plus hours of life in it. That's usually not what fails. It's the rest of the packaging that fails, and that's why your LED bulb eventually dies. So the chip is typically there, again, all the standard pieces of the architecture, level 1, wire bonds. There's heat is a big problem. Not only does it give out photons, it also gives out phonons. So you got to get that heat out of that little bulb. So that's why that big heat slug is over there. And then the leads, just electrical interconnections. So that's think about that as your level 2. And then the package is molded, and then you put some kind of a lens, clear or transparent lens. It's usually some kind of a polymer lens that's put on it. Okay. And then depending on what chip you're putting, you've got yellow LED, blue LED, green LED, and so on. Okay, so what degrades over here? All the standard suspects. The die attach is a problem. The wire bonds are a problem. The attach further below between the heat slug and the substrate is a problem. The lens is a big problem. And then we'll talk about a particular commercial white light technology is to use phosphors. They use the phosphor to convert blue light into white light because the phosphor absorbs all the photons and re-emits it as white light. That phosphor degrades over time. So then what happens is what you bought as white LED slowly, or a warm white LED, slowly turns bluer and bluer and bluer because the phosphor is degrading. Okay. And then the lens also degrades, gets yellowish with time. Because of this strong photo exposure, there's photo degradation of the polymer there. Okay. And here, these are Professor Hunt's slides. He does a nice job. Actually, I've removed a lot of his slides. He defines all the standard terminology. How do you measure the efficiency? What are the units of measurement? So the outputs come in lumens or lux or candelas, depending on what the units of measurement are and what aspect of the intensity you're measuring. So he has defined all of those, and I've put that as backup slides in your handouts. I'm not going to go through all of that. We just don't have the time. Okay, but basically, in this one, he's just simply saying, well, you supply power to the LED chip and electrons, and they're basically helping recombine the internal charge carriers and emitting photons. So you know how much electrical energy you're putting into it, and you know how much light is coming out. Again, that's why the units of measurement are important. So that's called radiometry or photogrammetry. Okay, so that's where you measure how many lumens, how many luxes, how many candelas. So that's how you measure the energy coming out. And knowing the energy that's gone in and the energy that's coming out, you can calculate efficiencies. Okay. And there are two aspects to that efficiency. That's what this slide is trying to show. One is the conversion from high energy electrons that you're putting in to high energy photons that are going to come out. That's your semiconductor level recombination. That's this stage. That's this stage. So there's an efficiency of that process. So how many photons come out for the amount of electrons that you're putting in. That's the internal quantum efficiency. And then after the photons are generated, how effectively are you extracting them out as usable light? So that's extraction efficiency. That the packaging plays a big role in that also. So together they give you the total efficiency or the external efficiency, and that is measured as, again, I have to double check the units, but I think that's in lumens per watts. So the output is measured, output energy is measured in lumens, input energy is measured in watts, so lumens per watts is the efficiency, okay? So he calls that the luminous efficacy. Okay, let's move on here. So white light. How do we make white light? As I said, either you take multiple colored LEDs, blue LEDs, red LEDs, green LEDs, and when you mix them in the right ratio, you get white light. As you know, that's your standard RGB mix, right? So you need multiple LEDs to make white light in that technology. Or you do this phosphor technology where you, let's go to the next page. So you cover your LED device, semiconductor device, with specially tailored phosphor layers. And now what's happening, the photons, and this is typically a blue LED, the photons of blue frequency that are coming out here are getting absorbed into the phosphor layer. And the phosphor absorbs it, gets energized, and re-emits new photons that are wideband spectrum, so it looks white. Okay. Okay. So that's what it's doing. It's absorbing blue light and then emitting light that looks much whiter, and that shift in frequency of the emission compared to the absorption of phosphor is usually called the Stokes shift. Okay. But again, there's losses in that process. You can see there's energy losses in that process. There's an efficiency loss for that part of the process also. Okay. And that excess loss is, of course, coming out as heat. So the phosphor is generating a lot of the heat, heating up increasing the junction temperatures and so on. Okay. And the phenomenon of that, by the way, is called photoluminescence. It's you're exciting it one kind of energy and one frequency of energy, and it's absorbing it and re-emitting a different frequency. That's photoluminescence. Okay. Okay. So here's what the phosphor converted light does. This is again Dr. Hahn's chart. I'll explain to you the message that he intends to give here. So you put the phosphor layer on top of a blue LED chip. Okay. So there's the blue LED chip and the phosphor layer on top of that. So this is sending blue photons into the phosphor. The phosphor is absorbing it, and it has partial efficiency. It's giving out heat and photons, and the photons that it gives out, partially it lets through just the blue ones. It's not able to convert everything, so that's leaked blue light. Okay, that's just a frequency response spectrum. Okay, so that's blue frequency, and part of it it's able to convert. Now you can see the frequency of that is much higher and broader. This is more broadband, so it looks whitish. Okay, so and this is actually still not quite white. What it does is when this color, whatever it is, converted color, recombines with this blue that didn't get converted. So that's the blue that didn't get converted. This is the converted light, which is not blue anymore, but some mix of other colors. When those recombine, you get basically color that's very close to white. Okay, that's the spectrum of white light that you get out of LEDs. It's bimodal. That's the nature of all LED light. You'll find that it's a bimodal spectrum distribution. Okay. Okay, and then depending on how much blue you're leaving in versus what percentage you're able to convert, more you convert, warmer the color. So you buy daylight white, you buy warm white, which is more yellowish, right? So the daylight white has less conversion, more blue in it. The warm whites have more conversion, less blue in it, basically. Okay. All right. And here's the colors. So in the LED world, colors are designated by temperature. Okay, it's called CCT, correlated color temperatures. So you can see red is somewhere around about 2200 Kelvin. Okay, 27 yellow, which is our normal incandescent bulb color, that's about 2700 Kelvin in this color chart, color correlation chart. Halogen lamps are about, as you get towards whiter and whiter light, it's about 3000 Kelvin. White light is about 4000 Kelvin, okay? And then by the time you get to the blues and ultraviolets, you're at about 5000 plus Kelvin, okay? That's the standard chart. It's an industry standard that was developed many years ago. Everyone uses that correlation. And you can see this would be, so 2700 would be down here, a little yellowish white light, okay? So that's yellowish. 3500 is slightly whiter. 3500 is up around here, slightly whiter, less yellow. And then by the time you get to 5500, it's a kind of a bluish white light. That's a bluish white LED light. Okay.
Do this follow Wales displacement
law, which is lambda T equals to constant?
The conversion comes from there, but it's a little more complicated. The equation is a little more complicated than that. Okay. And then there's this so-called color rendering index, which is a more of a, I wouldn't say subjective, but a more arbitrary scale. Okay, it's numbers go from 0 to 100, color rendering index, and it's the ability. Okay, it's some kind of a arbitrary quantitative measure of the ability of a light source to reproduce colors, not distort them. Okay, so in the sense, if you look at yourself in the mirror in this light, your skin appears to have a certain kind of a tone. You look at yourself in a yellow incandescent bulb light, your skin appears to have a different tone. That's the color. That is color rendering index. Okay, so you can see a 52 CRI light would make a skin tone look like that. The frequencies are the same, 3000 Kelvin. I mean, the color of the light is about the same, but the nature of it has to do with the spectral distribution around that around that temperature, okay, or around that frequency. Whereas 3000 Kelvin, that means same frequency, but a higher CRI makes your skin tone look different. Okay, so it's not just the color, which the example I gave was color from blue light to yellow light, but even within blue light, depending on what the shape of the spectral plot is, what the shape of that spectral plot is, the color rendering index varies. Okay, so all of these are specs. So if you buy an LED lamp, or you're going to spec an LED lamp, you would say what frequencies you want, what